Hello, everyone. Welcome to pre-lecture 24. This is going to cover our introduction to chapter 17, which is oxidation reduction reactions. So in oxidation reduction reaction, or sometimes called redox reaction, involves the transfer of electrons between our reactants and then making different species that are products. Okay. You can't have one without the other, so if something is reduced, something must also be then oxidized. A reminder from Gen Chem 1 that reduction, or when something is reduced, means it is gaining an electron or multiple electrons possibly, and oxidation means the loss of electrons. So you can remember oil rig as an acronym for oxidation is lost, reduction is gain, and those, of course, refer to electrons. Okay? Within redox reactions, the thing that gains electrons is the oxidizing reagent, and the compound that loses electrons is called the reducing agent. Something that might be confusing is that if something gains electrons, that means that the oxidizing reagent is reduced, and the reducing agent is then oxidized as part of a redox reaction. So make sure you get that terminology straight in your own head. And then why do we care about these? Redox reactions are extremely important for the construction of batteries and also in a lot of biological processes. So within biology, we have a lot of electrons moving around, and so tracking those redox processes is very important as well. Let's start by learning how to determine the oxidation state of elements. And so we track what is reduced and what is oxidized in a redox reaction by assigning oxidation states to elements within those compounds. And this can be done systematically following some rules. And so the first rule is that free elements, so elements that are just themselves, have an oxidation state of 0. This is also true for diatomic elements, so like Cl2. Cl would have an oxidation state of 0 in that case, despite there being 2 atoms, because it is only a single element that is still an oxidation state of 0. Next up, anytime we have a monoatomic ion, again, that's something with a positive or negative charge, the oxidation state is equal to that charge. And so the oxidation state of all of the atoms in a compound is 0 if it is neutral. And if it's a polyatomic ion, then the sum of the oxidation states in atoms will equal the charge of the ion. Okay. Third rule is that group 1 and 2 metals have an oxidation state corresponding to their place on the periodic table. So an example would be sodium is in group 1. That means it will always have an oxidation state of +1, unless it is just pure sodium metal. Another example would be magnesium. Then group 2, it will always have 2+, right? Next up, we have some elements that pretty much always have the same charge. The most predominant of these is fluorine. It's always going to have a charge of -1. Hydrogen should almost always have a charge of +1. Oxygen has a charge of 2-, unless it is a peroxide, meaning that we have 2 oxygens bound together. And like hydrogen peroxide, H2O2 would be an example of this. In that case, it would have an oxidation state of -1. And then group 17, so our halogens have a charge of -1. Group 16 have a charge of -2. Group 15 have a charge of -3. Something that I don't believe I've stated yet is that the order in which I'm giving you these rules also matter. And so, for example, rule number 1 and 2 are going to be more important than rules 3 and 4 in assigning oxidation states. And we'll have lots of practice with this, so hopefully it'll make some sense once we get into an example. Finally, last rule, all other element oxidation states are calculated based on what is left over. And so, again, hopefully this will make sense with an example, but these are our rules for determining an oxidation state. Once we determine the oxidation states of elements, we might have to balance a redox reaction. And this can also be done in a systematic manner. And so to start, you want to assign oxidation numbers. So use the rules on the previous slide to do that. Determine which element is oxidized and which is reduced. Then you want to break the original redox reaction into two separate reactions, including the electrons that are present. And then your first step should be balance the elements that are oxidized and reduced, and then balance the oxidation states by adding electrons. And so that would be how you do step 2. Step 3, then balance the charge of the half reactions. And so the charge needs to be the same on both sides of the reaction. I will also specify whether you should balance something in acidic solution or basic solution. With acidic solution, you want to add protons, H+. With basic solution, you want to add OH-. And then after we do that, we can balance our oxygen atoms and H atoms by adding water, H2O, to whichever side needs it. Then we would balance our electrons between our two half reactions in order to make them equal. And finally, add those half reactions together, add phase labels, and that should be our balanced reaction. But of course, we would want to check that all of our atoms are balanced and charges are also balanced. And so again, we'll go through an example of this right now so that hopefully it makes a bit more sense. And so let's say we want to balance the reaction shown here where we have BrO3- reacting with N2H4 to make Br- and N2. And so I'm going to start this by assigning oxidation states, and then we will balance the redox reaction. And so starting with oxidation states, just looking at our first species here, I know that according to one of our rules, oxygen should always be 2-. And so if we have 2- and we have 3 oxygens, that means that's a total of 6- charge. And then if our overall polyatomic ion charge is -1, then I can assign the oxidation state of bromine to be 5+. Okay, that would be how we figured that one out. If we look at our other species, N2H4, we know H should always be +1, and we have 4 of them. So that makes a total of +4. And then N2, so we have 2 nitrogens, and we have a neutral charge, no charge on that molecule. And so we need N2 to balance out to be -4 total. And so it's supposed to be -4 total to balance +4 from our hydrogens. Because we have 2 nitrogens, we would divide that by 2. And so each nitrogen would have a charge of 2-. Okay, so that is our reactants for our products. A little bit simpler. So Br-, any monoatomic ion is just the oxidation state is its charge. So Br- becomes -1. And N2 is a pure element without a charge, and any pure element without a charge has oxidation state of 0. Okay, and so those are the species basically. And so let me change my color here and we can do our balancing of our redox reaction. So if we're looking at then to figure out what is oxidized, what is reduced, bromine is going to go from +5 to -1. And if it becomes more negative, we know it's reduced. So I'm going to rewrite our reduction half reaction here, and I'm going to say BrO3- turns into Br-. And so in order to do this, we need to balance the electrons as well. And so if it goes from +5 to -1, that means we have 6 electrons on our reactant side, because that is the side that is more positive. Our electrons always go on the side that is more positive because electrons are negative, right? So we have 6 electrons. Now we want to balance our charge of the reaction by adding protons, because we're in acidic media. So if we want to balance that charge, we have a charge of 7- on our reactant side between our 2 reactants, electrons and BrO3-. And we have a charge of -1 on our product side. And so -7 and -1 has a difference of 6. And so that would be 6H+. When we do that, we then have a charge of -1 on both our reactants and our product set. Then finally, we have to balance our oxygens and hydrogens by adding water. And so we have 3 oxygens. I tend to just look to balance the oxygens with water, and the hydrogens should follow suit. And so if we have 3 oxygens, that means we should need 3 moles of water. We can double check our hydrogens. If we have 3 waters, that would be 6 hydrogens on our product side, 6 hydrogens on our reactant side. So our reduction half reaction should be balanced. We also then need to do our oxidation half reaction. And so the oxidation half reaction should be our other species, where we have N2, which is a charge of 2-, right? Each nitrogen going from 2- to 0. And so that is becoming more positive, meaning it is oxidized. And so it will be N2H2 turning into N2. Again, we want to go to the side that is most positive. And so we end up, so we start with N2, or we have 2 nitrogens, so our elements are balanced on each side as far as non-hydrogen and oxygen. And then we need to put our electrons on our product side because this is an oxidation reaction. Because we're going from overall a charge of 4- to a charge of 0, we need 4 electrons to do that, okay? And so if we add those 4 electrons, we can then balance the charge by adding our protons. And because our reactant side is neutral, product side is 4-, we need 4 positive charges in form of 4 protons to even that charge. And then we can check to see if we need to add water. In this case, we don't have any oxygen. We don't need to balance oxygens. We have 4 protons on one side, 4 protons on the other. And it would also help if I wrote the correct chemical name there. So it is an N2H2, N2H4, if you actually look at the problem. So sorry about that. So our protons are balanced as well. Okay, so last thing is we need to balance our number of electrons. So our top reaction has 6 electrons. Our bottom reaction has 4. And so if we multiply this top reaction by 2, this bottom reaction by 3, we would get 12 electrons on each side, which would then balance, of course. And so if we do this, this would then be 12H plus 2Br3-, 2Br- and 6H2O. And then on our oxidation half reaction, we would end with 3N2H4, 3N2, and 12H plus. The reason I leave out the electrons is because we know they're then balanced once we multiply that. And then hopefully you can see that we have 12H plus on our reactant side. In our reduction half reaction, we have 12H plus on our product side for our oxidation half reaction. So those will actually also cancel out. So we've canceled electrons, we've canceled protons. We can combine things back together then. And so this final reaction, what our final answer should be, is 2Br3- plus 3N2H4 yields 2Br- plus 3N2 plus 6H2O. Okay, and we can double check things, make sure they're still balanced. I will tell you that they still are balanced with all the elements. And so we know that that is our balanced oxidation reduction half reaction. So we'll be doing more of these in class, but hopefully that was a good introduction. If you do have any questions, please let me know. Otherwise, have a balanced day, and I will see you in class.